Hello, friends. Welcome back. Or if this is the first time you found your way here, welcome. Make yourself comfortable. Dim the lights a little. Settle in. Look up tonight if you can. Find one star, just one, and ask yourself something simple. Ask how far away is that most people have heard the answer before. A few light years. Someone says like that explains everything, and we nod, we accept it. We move on. But what if that number, that quietly enormous number, is something you have never truly felt before? Before we drift into the dark together, if these slow, quiet journeys bring you something, a little wonder, a little calm, you might like to stay a while. You can gently tap the like button just to say, I was here tonight. And if you'd like more stories told softly in the spaces between waking and sleep, you're welcome to subscribe. Ring the little bell not for noise, but so the next quiet night can find you again. Now, let's begin. There is a mistake almost everyone makes. It is not a dramatic mistake. No one is embarrassed by it. It hides inside a word that sounds perfectly clear. A word you have probably used yourself, maybe in school, maybe reading about galaxies on a lazy afternoon. The word is light year. And the mistake is this: most people somewhere in the back of their minds believe that a light year is a measure of time. It sounds like time, doesn't it? A year is time. So a light year must be a very bright year, perhaps. A year measured somehow in starlight. The brain fills in the gaps the way brains always do, quietly, confidently, and sometimes completely wrong. A light year is not time at all. It is distance. It is the distance that light, the fastest thing in the known universe, travels in one full year of moving, without stopping, without slowing, without rest. Let that settle for a moment. Light moves at roughly 186,000 miles per second, not per hour, not per minute, per second. In the time it takes your heart to beat, once light has traveled a distance that would circle the Earth more than 7 times, in 1 second. Before your heart beats again, it has done it 7 more times. Now, imagine that speed, that almost incomprehensible speed, running without pause for 365 days and nights. Running through January and February, through summer heat and autumn rain, through every quiet Tuesday and every sleepless night of an entire year. At the end of that year, light has traveled approximately 5.88 trillion miles. That is a light year, 5,880,000,000,000 miles. The number has 12 digits. Most numbers we deal with in a lifetime have 5 or 6. Our brains were not built for 12 digits. We were built for the savannah, for counting animals, for measuring fields, for distances we could walk in a day. 12 digits sits outside the reach of ordinary feeling. And yet, the nearest star to our sun, a small dim red dwarf called Proxima Centauri, sits 4.24 light years away. Not 1 trillion miles, not 5 trillion, more than 24 trillion miles away. And that is the closest one, the neighbor, the star next door. Pause here for just a breath. Have you ever looked at a photograph of the night sky? Really looked, not just glanced and felt something shift inside you? Something that was not quite fear and not quite awe, but something in between. Something your body recognized before your mind did. That feeling has a name in some languages. In German, there is a word, Weltschmerz, the ache of the world, the sadness that comes from understanding how large everything is. In Japanese, there is mono, know aware the gentle sadness of impermanence of things too beautiful to hold. English does not have a single word for the feeling of standing under a night sky and suddenly truly understanding that the light you are seeing left its source before you were born, before your parents were born, before their parents were born. But the body knows it. The body has always known it. Now here is where this story gets interesting. And by interesting, I mean quietly unsettling in the best possible way. We know what a light year is. We can write the number down. We can say it out loud. But knowing a number and feeling a number are 2 entirely different things. And the gap between those 2 things is where most of us have been living our whole lives without realizing it. So, Let us try something different tonight. Let us not just say the number, let us try to walk it. Not literally, of course, but in imagination, which is the only vehicle most of us will ever have for distances like these. Let us try to understand what it would actually mean for a human being to cross 1 light year. Not to think about it, not to read about it, to go, to actually go. What would it cost? What would it take? How long would it really be? This question seems simple. It is not simple. It turns out to be one of the most beautiful, strange, and quietly heartbreaking questions you can ask about the human condition. Because when you ask how long it would take humans to cross a light year, you are not just asking a math problem. You are asking, what are we really in the scale of what exists? You are asking whether the universe was made for us or whether we are simply the part of it that became aware enough to wonder. And the answer, when we follow it carefully, leads somewhere unexpected. It leads not to despair, but to something that feels in the end very much like home. Let me start at the beginning. Not the beginning of space travel, but the beginning of the question itself. The moment in human history when someone first looked up and tried seriously to understand how far away things really were. For most of human history, the stars were simply there. They were lanterns. They were gods. They were the fixed backdrop against which the drama of human life played out. No one seriously asked how far they were, because the answer seemed obvious. They were up there, and we were down here, and the distance was simply the distance between mortals and the divine. The ancient Greeks were the first to begin measuring, and they were remarkable. Around 240 BCE, a man named Eratosthenes, a librarian in Alexandria of all things, calculated the circumference of the Earth using nothing but a stick, a shadow, and the position of the sun in 2 different cities. He was accurate to within a few percent. Using shadows and geometry standing in a library, he measured the planet beneath his feet. But the stars remained beyond reach. They were too far for any shadow to fall, meaningfully too distant for the geometry of the ancient world to grasp. It was not until 1838 that a German astronomer named Friedrich Bessel made the first successful measurement of a stellar distance, the distance to a star, called 61 Cygni. He did it using a technique called parallax, holding up a finger, and closing each eye. Alternately, the finger seems to shift against the background. Do the same with a nearby star, observed from opposite ends of Earth's orbit around the sun. And the star also appears to shift very slightly, almost imperceptibly, against the more distant background stars. From that shift, you can calculate the distance. 61 Cygni was approximately 11 light-years away. Bessel spent months making these measurements. He tracked the sky through winter and through summer, taking readings with instruments of extraordinary delicacy for his time. And when he published his result, the scientific world was staggered. Not because the number was unexpected, but because for the first time, the number was real. Someone had reached out with mathematics and actually touched a star. The emotional weight of that moment is hard to overstate. For thousands of years, the stars were infinite and untouchable. Then one man with a telescope and a notebook in 1838 put a number on one of them, and the infinite became, for the first time, merely very, very large. Now there is something I want you to notice about what Bessel did. He did not travel anywhere. He did not send anything. He did not build a rocket or design an engine. He simply looked very carefully from 2 different positions and let mathematics do the rest. And this is in many ways the story of humanity's relationship with interstellar distance. In a single image, we have always been better at measuring the gap than crossing it. We can describe it with precision. We can write it in 12 digits. We can point to it on a map of the galaxy. What we cannot do, what we have never done, not even remotely, is actually go. The fastest spacecraft ever launched from Earth is NASA's Parker Solar Probe, which in recent years has reached speeds approaching 430,000 miles per hour during its close approaches to the Sun. That sounds extraordinary. It is extraordinary. It is the fastest thing human hands have ever built. At that speed, crossing 1 light-year would take approximately 1,500 years, not 1,500 days. Not 1,500 months, 1,500 years. The Roman Empire fell roughly 1,500 years ago. The Mayan civilization was flourishing 1,500 years ago. The first Islamic caliphate was being established 1,500 years ago. If we had launched a spacecraft toward the nearest star, at the moment the Roman Empire collapsed, it would still be traveling now, and it would not yet be even halfway there. Let that sit for a moment, just a moment. And yet here is the turn. Here is the thing that makes this question not sad but luminous. Humans did not stop at measuring. We never do. Eratosthenes did not accept that the size of the Earth was unknowable. Bessel did not accept that the stars were untouchable. And the generations of scientists and dreamers who came after did not accept that the galaxy was permanently beyond reach. They started asking, what if we built something faster? What if we learned to use something other than fuel, something like light itself, like the pressure of starlight pushing against a sail? What if the distance is not the problem, but only our speed? And speed is something that, in theory, can always be increased. What if the real barrier is not physics, but only time and will? That question is alive right now, in laboratories and in the minds of physicists who have dedicated their lives to it. And tonight we are going to follow it all the way, from the first step to the last, from a walking pace to the edge of what Einstein's universe will allow. So, take a breath, rest your eyes. We are not going anywhere quickly. That, as you will come to understand, has always been part of the beauty. We have only just begun, and already the universe has quietly rearranged something inside the way you see that single star. In a moment, we will do the mathematics that most textbooks skip. What would actually happen if a human being tried to walk a light year step by step at the ordinary pace of a life? The numbers are patient, and they are waiting. So, we said the number, 5.88 trillion miles. We said it carefully, we let it land. And most of us nodded the way you nod at something you cannot truly imagine, but are willing to accept on good faith. But here is what I want to try tonight. Not just to say it, to build it. Slowly from the ground up, the way a child builds a tower of blocks not to impress anyone, but just to see how high it goes before it stops making sense. Because there is a difference between a number you know and a number you feel. And almost no one has ever truly felt a light year. Not even the astronomers who work with them every day. They will tell you this themselves in quiet moments when the math stops and the wonder starts. Let us begin with something your body already understands. A mile. You know a mile. If you have ever walked a mile down a road around a park through a neighborhood on a slow evening, your legs remember it. About 15 to 20 minutes of easy walking. Your body carries that memory. A mile is real. Now, let us move one step larger. The distance from New York City to Los Angeles is approximately 2,800 miles. If you drove it without stopping, no sleep, no food, just the highway unrolling ahead of you at 70 miles per hour, it would take about 40 hours, 2 days of continuous driving. Most people who have made a long road trip somewhere carry a physical sense of that kind of distance. It is large but manageable. The mind can hold it. Now the moon. The moon sits about 239,000 miles from Earth. The Apollo astronauts traveled that distance in roughly 3 days. 3 days is something we understand: a long weekend, a short trip, the time between Monday and Thursday. The moon is far, but it is graspable far. Mars, at its closest approach to Earth, is about 34 million miles away. A spacecraft traveling at a typical speed would take around 7 months to get there. 7 months is a pregnancy. It is a school semester. It is the time between spring and winter. Still graspable. Barely, but still. The sun is 93 million miles away. Light from the sun reaches your skin in about 8 minutes and 20 seconds. That warm feeling on a summer afternoon is 8-minute-old light. Your body is touching something that left the sun while you were still making coffee. Now, we leave the neighborhood. The outer edge of our solar system, the boundary where the sun's influence fades into the cold of interstellar space, a region called the heliopause, sits about 11 billion miles from Earth. 11 billion. Voyager 1 launched in 1977, reached that boundary in 2012. It took 35 years of constant travel at roughly 38,000 miles per hour just to reach the edge of our own solar system. And a light year is not 11 billion miles. A light year is 588 times farther than that. So, if we imagine the entire journey of Voyager 1, all 35 years of it, the entire span of a human career, the entire childhood and adolescence of a person born, the year it launched, now a middle-aged adult. If we shrink all of that down into a single step, a light year is still 588 steps away. Does the number have a face yet? Not quite. Let us keep building. Here is a comparison that some astronomers use when they are trying to explain scale to people who are not astronomers. And I find it one of the most quietly devastating images in all of science. Imagine the entire solar system. The Sun, all 8 planets, the asteroid belt, the distant Kuiper belts of frozen objects beyond Neptune. Imagine all of that shrunk down to the size of a single coin. A quarter, let us say. The kind you find at the bottom of a bag. On that same scale, the nearest star Proxima Centauri, 4.24 light-years away, would be located approximately 1.6 miles from your coin. So, you are holding our entire solar system in the palm of your hand, and the nearest neighbor is 1.5 miles down the road. And between your hand and that neighbor, nothing. Empty space, not almost nothing, truly measurably, achingly nothing. The void between stars is so complete that it makes the space between planets look crowded. Now consider that the Milky Way galaxy, our galaxy, the one we live inside, contains somewhere between 100 and 400 billion stars, and most of them are separated by distances in that same range, a few light years, sometimes tens of light years. Coins scattered across a continent, each one miles from the next, and the continent itself stretching for distances that make the word large feel embarrassed. And the Milky Way is one galaxy among an estimated 2 trillion in the observable universe. 2 trillion galaxies, each containing hundreds of billions of stars, each star separated from its neighbors by trillions of miles of silence. This is the universe we live in. This is the house. And we are all of us, every human being who has ever lived, every city ever built, every song ever sung. We are on one small rock orbiting one ordinary star in one unremarkable corner of one of 2 trillion galaxies. There is a question hiding in that image. You can feel it, can't you? It is the question this entire night is circling, the one we will keep returning to from different directions. Not, are we alone, though that is part of it, but something quieter, something more personal. Does the distance mean we are small, or does it mean something else entirely? Hold that question. We will come back to it. Now, I want to talk about a common mistake, not the light year as time mistake we discussed before, but a subtler one that even careful, curious people make. When most people try to imagine interstellar distance, they instinctively reach for time as a way to make it feel real. They say, well, if light takes 4.24 years to get there, and we're slower than light, it would take us much longer. And that is true. But the mistake is in thinking that longer is the only dimension that changes. What actually happens when you try to cross interstellar space is not just that the journey takes more time. It is that the journey is more time. At the speeds we can currently achieve, the journey to the nearest star does not take a lifetime. It takes many lifetimes stacked one on top of another, like geological layers, more lifetimes than recorded human history contains. We will do those exact numbers together in a little while. But first, I want you to sit with the pure geometry of it without the math. I want you to feel the shape before we measure it. Think about the deepest time you have ever personally experienced. Maybe it is a memory from early childhood. So far back it feels like a story someone else told you. Maybe it is a photograph of a great-grandparent you never met, holding a child who would become your grandparent, a whole generation compressed into a single sepia rectangle. Maybe it is standing in a cathedral built in the 12th century, touching stone that was cut and placed by hands 800 years before yours. That feeling, that vertigo of time, is what interstellar distance actually is. Not space, time. They are the same fabric as Einstein spent his life trying to tell us. And distance in space is always also distance in time. When you look at Proxima Centauri, when you find it with a telescope on a clear night, a faint red point in the southern sky, the light entering your eye left that star 4.2 4 years ago. You are not seeing it as it is. You are seeing it as it was when 4.24 years of your life ago had not yet happened. If something changed at Proxima Centauri today, if it flared, if it shifted, if something extraordinary happened at this very moment, you would not know for 4.24 years. The message is already traveling, you just have not received it yet, and that is the nearest star, the Andromeda Galaxy, the closest large galaxy to our own visible to the naked eye as a faint smear of light on a very dark night, is 2.537 million light-years away. The light you see when you look at Andromeda left its source 2.537 million years ago. At that moment, our ancestors were small, upright walking primates on the African savanna. Homo sapiens did not yet exist. The light that entered your eyes tonight began its journey before our species did. There is a physicist and author named Brian Greene who once described the night sky as a time machine, not a metaphor, but a literal description of what you are doing when you look up. Every point of light is a different moment in the past. Some stars you see may no longer exist. They burned out, collapsed, or exploded centuries or millennia ago, and the news simply has not reached us yet. We are surrounded every night by ghosts that do not know they are gone. I find that one of the most beautiful and quietly unsettling ideas in all of science. The sky is not a snapshot of now. It is a collage of thens. 1,000 different pasts all arriving at your eyes simultaneously from 1,000 different distances. Like letters from friends who all mailed them at different times. And they all happen to arrive on the same afternoon. Have you ever received a letter, a real physical letter from someone who sent it weeks ago? And by the time it arrived, everything they described had already changed. The situation they were worried about had resolved. The thing they were celebrating had already passed. You were reading a moment that no longer existed preserved in ink and paper, like an insect in amber. That is what stargazing is, every single night. Now, I want to offer you something that might change the way you think about this number permanently. Not a fact exactly, but a frame. A way of holding the scale that makes it not crushing, but in a strange way, clarifying. In 1977, NASA launched two spacecraft, Voyager 1 and Voyager 2. They were sent to study the outer planets, Jupiter, Saturn, Uranus, Neptune, and then to keep going into interstellar space for as long as their power lasted, and as long as we could maintain contact. In 1990, when Voyager 1 was about 3.7 billion miles from Earth, still inside our solar system, still not even close to the heliopause, the astronomer Carl Sagan made a request. He asked NASA to turn Voyager's camera around and take one last photograph of Earth before the camera was shut down to conserve power. The result was an image called the pale blue dot. In that photograph, Earth appears as a tiny point of light, a fraction of a pixel barely distinguishable from the scattered light around it, suspended in a beam of sunlight against the black of space. The entire planet. Every mountain, every ocean, every city, every person who ever lived or will ever live. A pale blue dot. Carl Sagan wrote about that image in a way that has never quite left me. He wrote that it underscores the responsibility we bear toward one another and the foolishness of our conflicts over this pale blue dot, this tiny stage in a vast cosmic arena. But here is what I want you to notice, the thing Sagan's words point toward, but do not say directly. That photograph was taken from 3.7 billion miles away. 1 light year is 5.88 trillion miles. The photograph was taken from less than 1/10 of 1% of a light year away. We had not even left the driveway, And already Earth was invisible. Already the only home our species has ever known had shrunk to something you could cover with the point of a pin. So, when we ask how long it would take humans to cross a light year, we are not just asking about engines and fuel and speed. We are asking something deeper. We are asking what it would mean to leave that pale blue dot so far behind that not only could you not see it, you could not even find the sun. It orbits without a star chart and a telescope. We are asking what it means to be truly, completely, irreversibly away. And the mathematics of that question, the cold patient, beautiful mathematics are just ahead of us now. We have built the scale. We have felt the shape of it. Now it is time to do the walk, step by step, mile by mile, year by year. The numbers, when we finally do them together, will surprise you. Not because they are larger than you expected, but because of what they reveal about the strange, quiet courage of a species that keeps asking the question anyway. So, let us do the walk, not metaphorically, not approximately. Let us sit down together and do the actual arithmetic, the kind that textbooks skip, because it makes the numbers feel too heavy, too personal, too close to something the rational mind would rather not look at directly. Because here is a thing I have noticed about science education. We are very good at giving people numbers and very bad at giving people the weight of those numbers. We say 5.88 trillion miles and move on. We say it would take a very long time and change the subject. We protect people from the full arithmetic the way you might protect a child from a truth they are not quite ready to hear. But you are here at this quiet hour, and I think you are ready. So, let us not look away. A healthy adult walking at a comfortable pace covers roughly 3 to 4 miles per hour. Let us be generous and say 3.5 miles per hour, a pleasant stroll, the kind you take on a cool evening when there is no particular destination, just the pleasure of moving through air. At that pace, you cover 84 miles in a single 24-hour day, assuming you never stop. No sleep, no food, no rest. Just walking continuously through every hour of every day. That gives us 30,660 miles in a year of constant walking. 1 light year is 5,880,000,000,000 miles. So to walk 1 light year at a comfortable human pace, it would take approximately 192 million years. 192 million years. Let that number breathe for a moment. Do not rush past it. Sit with it the way you would sit with a piece of music that ends in a chord you did not expect. 192 million years ago, dinosaurs had not yet reached their peak dominance on Earth. The supercontinent Pangaea was still in the early stages of breaking apart. The Atlantic Ocean did not exist. The land that would become North America and the land that would become Europe were still touching, still pressed together like the pages of a book not yet opened. The first small mammals were only just beginning to appear timid and nocturnal, hiding in the shadows of giants. If our walking ancestor had set off from Earth at the moment, those first small mammals took their first nervous steps and had walked without pause through the entire age of dinosaurs, through the asteroid impact that ended them, through the long, slow rise of mammals, through the emergence of primates, through the entire evolutionary journey from those small, trembling creatures to the person sitting here right now, listening to these words, they would still not have arrived. They would be about halfway. Now, I want to be very precise here because precision is where the awe lives. 192 million years is not just a long time in some vague hand-waving sense. Let us compare it to things that feel historically significant, things that carry emotional weight that we have heard about and read about and built museums around. The entire recorded history of human civilization, from the first writing in ancient Sumer, roughly 5,000 years ago, to this very moment, represents about 5,000 years. That is the full span of everything we call history. Every empire, every war, every discovery, every artwork, every love letter, every revolution. 5,000 years. Our walking journey to the nearest star would take 192 million years. That means recorded human civilization, the entire arc of everything we know as human achievement, represents about 0.0026% of the journey. Not even a rounding error of a rounding error. Or think of it this way. If the walking journey were compressed into a single calendar, year January 1st to December 31st, recorded human history would occupy the final zero point 0.8 seconds of December 31st, a single breath before midnight. Everything you have ever learned about every historical figure you were taught about in school, every civilization that rose and fell, contained in less than 1 second at the very end of a year-long journey. Does that feel wrong? Does some part of you resist it? Good. That resistance is healthy. It means you are actually trying to feel the number rather than just accepting it. Most people accept it and move on, and by doing so, they never actually understand it. There is a classic thought experiment that physicists and science writers sometimes use to illustrate deep time, and I want to adapt it here for our walking journey because I think it is the most viscerally effective way to understand what 192 million years actually means to a human body and a human mind. Imagine you are going to walk this journey. You have committed. You pack lightly. There's no point in bringing much because everything you brought will have crumbled to dust long before you arrive, and you will need to resupply from whatever exists along the way. And whatever exists along the way will itself have changed beyond recognition many times over. You take your first step. In the first year of walking, you cover about 1,277 miles. You feel good. You are making progress. The math feels manageable. After 100 years of walking a full century longer than almost any human life, you have covered 127,750 miles. That is roughly half the distance to the moon. You have walked for 100 years and you have not yet left the neighborhood of the Earth. After 1,000 years of walking, you have covered about 1.28 million miles. You are now past the moon. You are somewhere in the vast emptiness between Earth and Mars. 1,000 years of walking longer than the span from the Norman conquest of England to today, and you are still in the inner solar system. After 10,000 years, the entire span from the first agricultural villages to the present, you have walked about 12.8 million miles, still well inside the solar system, still not yet to the orbit of Jupiter. After 100,000 years, roughly the time since modern humans first migrated out of Africa and began populating the rest of the planet, you have covered about 128 million miles. You are somewhere around the asteroid belt, still inside the solar system. The sun behind you still appears as a bright star, unmistakably the dominant light source in your sky. After 1 million years, you have walked roughly 1.28 billion miles. You are now somewhere in the outer solar system, perhaps near the orbit of Saturn. Behind you, the sun has shrunk to a very bright star, still clearly the sun, but no longer a disk, no longer the center of everything, just the brightest point in a field of points. After 10 million years, you have walked about 12.8 billion miles. You are now past the heliopause, past the boundary of the solar system, into true interstellar space. It took 10 million years of walking to leave our solar system. In those 10 million years on Earth, entire species would have evolved and gone extinct. The climate would have shifted through multiple ice ages. The continents would have moved measurably, perhaps by hundreds of miles. And you would have 182 million years of walking still ahead of you. Here is where I want to pause and ask you something. And I mean this as a genuine question, not a rhetorical flourish. What does that feel like to you? Not intellectually, not as a math problem, but as a feeling. When you try to hold 182 million more years of walking in your body, not just your mind. What happens? For most people, something unusual occurs. The number becomes so large that it stops feeling large. It becomes almost peaceful. Like standing at the edge of the ocean at night, the darkness goes on so far that fear becomes something else, becomes stillness, becomes a kind of surrender to the scale of things. I think that is not a failure of imagination. I think that is the imagination doing something very intelligent, recognizing that some things cannot be grasped in full and relaxing into that recognition rather than fighting it. The Zen Buddhist tradition has a concept sometimes translated as beginner's mind. The idea that the most useful stance towards something vast and complex is not mastery, but openness. Not, I understand this, but I am willing to be changed by it. The night sky has been producing beginner's mind in human beings for as long as there have been human beings to look up at it. Now, there is a common mistake I want to address directly, because it comes up every time someone encounters these numbers and starts doing their own arithmetic. The mistake is to assume that walking pace is such an absurd baseline that the calculation is not meaningful. Of course, walking is impossibly slow, someone might say. What if we drove? What if we flew? The real question is what we can do with technology. And that is a fair objection. We will get to technology. We will get to rockets and ion drives and light sails and all the extraordinary things human ingenuity has imagined and built. But I want to make the case for the walking calculation because it contains something the technological calculations do not. The walking calculation is honest about the human body. Every other calculation, rocket, spacecraft, laser propulsion, abstracts the human being away. It turns the problem into an engineering question, a question of hardware and fuel and physics. The walking calculation refuses to do that. It keeps the human being in the frame. It says here is a person with legs and lungs and a heartbeat, and here is what this distance costs that person denominated in the currency of a human life. And that cost is not a failure. It is not an embarrassment. It is information. It is the universe telling us something true and important about the relationship between the scale of what exists and the scale of what we are. Think about it this way. When we look at the Grand Canyon, when we stand at the rim and look down at 2 billion years of geological history exposed in the colorful striated rock, we do not feel diminished by the fact that we could not have carved it. We feel something closer to reverence. We feel perhaps a kind of grateful smallness. The canyon is not a rebuke, it is a gift. The light year is the same kind of gift. But let us push the calculation a little further, because there is a twist in the numbers that most people never reach, and it changes the emotional texture of everything. So far, we have been assuming a single person walking. But what if we think about generations? What if we imagine a family? A lineage setting out on this walk and passing the journey from parent to child to grandchild. Generation after generation, the way certain cultures pass down oral traditions or sacred responsibilities. The average human generation is roughly 25 to 30 years. Let us say 25. At a walking pace, each generation covers about 32,000 miles before passing the journey on. How many generations would the walk require? 192 million years divided by 25 years per generation gives us approximately 7.68 million generations. For context, the entire evolutionary lineage from our earliest ape-like ancestors to modern humans spans roughly 200,000 to 300,000 generations. The walking journey to the nearest star would require about 25 to 30 times more generations than it took to evolve from a primate to a person. In those 68 million generations, assuming the walkers survived and continued to evolve, which biology strongly suggests the descendants arriving at Proxima Centauri would likely bear about as much resemblance to us as we bear to our primate ancestors. They would be human in some ancestral sense the way a great-great-grandchild is human in the same sense as their ancestor. But they would not be us, not in any meaningful, recognizable way. The journey would not just take a long time. It would transform the travelers entirely before they arrived. There is something in that thought that I find extraordinarily moving in the quiet way that certain scientific facts become unexpectedly personal. We tend to think of space travel as a project, something that starts and ends, something that has a crew, a mission statement, a return journey. We think of astronauts who leave and come back, heroes who kiss their families goodbye and come home with photographs and stories. But the walking calculation reveals a different kind of journey entirely. A journey so long that the concept of returning home becomes meaningless, because home would have changed beyond recognition or ceased to exist before anyone arrived anywhere. A journey so long that the travelers themselves would become something new, shaped by the way the void shapes everything it touches. There is a word for this in evolutionary biology founder effect. When a small population becomes isolated from the main population on an island in a valley, perhaps aboard a starship, the genetic diversity of that small group gradually diverges from the original. Over thousands of generations, they become something distinct, something new, something that could not have been predicted from the starting point. The stars, it turns out, are not just destinations, they are crucibles. The journey itself is the transformation. And this is why, when we start to think about what it would actually take to cross a light year, not in a thought experiment, but in reality, with real human beings, the question stops being purely mathematical and becomes something else entirely. It becomes a question about what it means to commit to something you will never see completed, about what it means to begin a journey whose end you will never know, about what kind of person, what kind of species chooses to start anyway. History, as it turns out, is full of them, and their stories are stranger and more beautiful than any rocket equation. The fastest things we have ever built are waiting just ahead, and when we hold them up against this walking calculation, against this honest accounting of human scale, something unexpected comes into focus, something that changes not just the numbers, but the question itself. So, the walking calculation has given us something honest, something grounded in the body, in the pace of a human life, in the quiet arithmetic of generations. And now, naturally, the mind wants to run, because that is what human beings do. We are not content with the pace we were given. We have never been. From the moment our ancestors looked at a river and thought I could cross that faster on a log, to the moment engineers at NASA watched a Saturn V rocket clear the launch tower and felt the ground shake beneath their feet. The entire arc of human technological history has been a single sustained argument against the limitations of the body. We want to go faster. We always have. The question is, how much faster have we actually managed? And when we hold our fastest achievements up against a light year, what do we see? Let us trace the arc, not just the numbers, but the story. Because the story of human speed is one of the most extraordinary narratives in all of history, and most people have only ever heard fragments of it. For the vast majority of human existence, for roughly 300,000 years, the fastest a person could travel was the speed of a running human, about 12 to 15 miles per hour at a full sprint, sustainable for only seconds. For longer distances, maybe 6 to 8 miles per hour on a horse, if you had one. For most of human history, most people never in their entire lives traveled faster than a cantering horse. That was the ceiling. That was the edge of the possible. Then, in the early 19th century, something broke open. The steam locomotive arrived. The first practical steam-powered railway, the Stockton and Darlington Railway in England, opened in 1825. It could move passengers at the astonishing speed of 15 miles per hour. People were genuinely frightened. Doctors wrote serious medical papers warning that traveling at such speeds might cause the human body to disintegrate, that the lungs could not handle air rushing in at that velocity, that the mind might snap under the strain of such unnatural motion. They were wrong, of course, but the fear is revealing. It tells us how completely 15 miles per hour exceeded the prior boundary of human experience. For 300,000 years, the ceiling had been roughly 15 miles per hour at a dead sprint for about 10 seconds. Now, a machine could sustain that speed for hours. It was not just faster travel, it was a different relationship with distance itself. Within decades, locomotives were reaching 60, then 80, then over 100 miles per hour. By the early 20th century, experimental steam locomotives were breaking 125 miles per hour. The ceiling kept rising faster than anyone had predicted, faster than the fearful doctors could update their warnings. Then came the automobile, the propeller aircraft, and eventually the jet engine. On October 14, 1947, a young Air Force test pilot named Chuck Yeager climbed into a small experimental aircraft called the Bell X-1, painted bright orange shaped roughly like a bullet, and dropped from the belly of a larger plane at high altitude, and did something that many serious engineers had believed was physically impossible. He pushed through the speed of sound, Mach 1, approximately 767 miles per hour at sea level. There was a theory taken seriously in some circles at the time that the sound barrier was not just a technical obstacle, but a physical wall that the shock waves building up at the nose of an aircraft at transonic speeds would tear any vehicle apart before it could break through. Some called it the sound barrier, with the same finality they might say brick wall. Yeager punched through it on a Tuesday morning. He had 2 broken ribs from a horse riding accident the weekend before, which he had not reported because he was afraid of being grounded. He used a piece of a broomstick to help him close the cockpit hatch because his injured arm lacked the strength. And then he flew faster than any human had ever flown, with 2 broken ribs and a broomstick, and the sky did not end. The sound barrier was not a wall, it was a door. And on the other side, the acceleration of human speed entered a phase that makes everything before it look geological in its slowness. Within a decade of Yeager's flight, jet aircraft were flying at Mach 2, then Mach 3, the SR-71. Blackbird, the fastest air-breathing aircraft ever built, first flew in 1964 and could sustain speeds of Mach 3.3, approximately 2,200 miles per hour, for extended periods at the edge of the atmosphere. It flew so fast that its titanium skin would heat to temperatures that required the airframe to be designed with small gaps to allow for thermal expansion. On the ground, those gaps meant the plane leaked fuel slightly. It only became fuel tight once it was flying fast enough to heat up. The SR-71 was in a literal sense only whole when it was moving. I find something deeply poetic about that. A machine that was only complete at full speed, a thing that needed its own velocity to hold itself together. But even the SR-71, even Mach 3.3, even 2,200 miles per hour, is still in the context of a light year essentially walking. At the SR-71's top speed, crossing 1 light year would take approximately 3 million years. We have gone from 192 million years walking to 3 million years in the fastest plane ever built. We have improved by a factor of about 64. The gap has narrowed from 192 million to 3 million, but it is still 3 million years. So we leave the atmosphere entirely. The first human-made object to reach orbital velocity was Sputnik 1, launched by the Soviet Union on October 4, 1957. It traveled at approximately 18,000 miles per hour, fast enough that the centrifugal force of its circular path balanced the pull of Earth's gravity, and it simply fell continuously around the planet without touching it. Orbital velocity is not really up, it is sideways very fast. Sputnik was falling toward Earth every moment, but moving sideways fast enough that Earth curved away beneath it at the same rate, 18,000 miles per hour. That sounds extraordinary. And in atmospheric terms, it is. But at 18,000 miles per hour, crossing 1 light year would take approximately 37,200 years. We are still talking about tens of thousands of years longer than all of recorded history. The Apollo missions that carried humans to the moon reached speeds of about 24,000 to 25,000 miles per hour during the translunar injection, burned the moment the rocket fires to break free of Earth's orbit and coast toward the moon. At that speed, a light year would take about 27,000 years, still longer than civilization. Here is the number I want you to hold, because it is the one that most accurately represents where humanity currently stands. Voyager 1, launched in 1977. The most distant human-made object ever built, now traveling through interstellar space, moves at approximately 38,000 miles per hour relative to the Sun. It reached this speed partly from its own rocket engines at launch, and partly from a technique called a gravitational slingshot, or gravity assist, flying close to a massive planet and using its gravity like a cosmic sling to add velocity without burning additional fuel. Voyager's gravitational slingshot, past Jupiter in 1979, added about 35,000 miles per hour to its speed. An invisible planet-sized hand reaching out at the dark and throwing a small metal spacecraft, faster than any rocket could on its own. The ingenuity of that maneuver, first proposed seriously by a graduate student named Gary Flandreau in 1965, who noticed that a rare alignment of the outer planets in the late 1970s would make it possible, is one of the quiet masterpieces of human engineering. At 38,000 miles per hour, Voyager would take approximately 17,500 years to travel 1 light year. And the nearest star, Proxima Centauri, 4.24 light-years away, would take Voyager roughly 73,000 to 80,000 years to reach. For context, Voyager is not headed toward Proxima Centauri. But if it were, and if it maintains contact, which it almost certainly will not, as its nuclear power source is expected to fail, sometime in the 2020s, the earliest possible arrival would be around the year 78,000 CE. When I think about Voyager right now, this small gold-plated disk of human music and mathematics, floating alone in the dark between stars, its plutonium heart slowly cooling its signal, taking over 22 hours at the speed of light to reach us, something in me goes very quiet. Something that is not sadness exactly, but is in the same family as sadness. We sent it. We made it. We gave it a golden record with the sounds of Earth whale songs, Beethoven, a baby, crying greetings in 55 languages. We said in the most human way possible we were here, and then we let it go into a silence so complete that no sound will ever reach it again. Now, I want to introduce a number that most people have not heard, and it will reframe everything we have discussed so far. In recent years, NASA's Parker Solar Probe has achieved speeds that dwarf everything that came before. During its closest approaches to the Sun, using the Sun's own gravity to accelerate the same slingshot principle Voyager used with Jupiter, but far more extreme, the Parker Solar Probe has reached speeds approaching 430,000 miles per hour. 430,000 miles per hour is about 11 times faster than Voyager. It is faster than anything humans have ever built. At that speed, you could travel from New York to Los Angeles in about 21 seconds. And at that speed, crossing 1 light year would take approximately 1,550 years. 1,550 years. The Roman Empire fell roughly 1,550 years ago. Pope Leo III crowned Charlemagne Holy Roman Emperor roughly 1,000 years before that event. We are still talking about timescales that swallow entire civilizations. But notice what has happened to the number. We started at 192 million years walking. The Parker Solar Probe gets us to 1,550 years. We have improved by a factor of roughly 124,000. We have compressed the journey by an enormous amount. And yet we are still talking about 1,550 years, still more than the entire span of the medieval period, still longer than the United States has existed by a factor of 7. Here's the question I want to sit with for a moment, and I mean it as a genuine puzzle, not a trick. Why does the gap between our best speed and the speed of light feel so discouraging, when in fact we have made such extraordinary progress? From 12 miles per hour to 430,000 miles per hour in 300,000 years, that is an improvement of 35,000 times. Why does it still feel like we are standing still relative to the stars? The answer is a mathematical concept called the exponential gap at the ceiling. When you are far from a limit, progress feels rapid and continuous. Every improvement seems significant because you are measuring it against where you started. But as you approach certain physical limits, and the speed of light is the hardest limit in the known universe, the gap between where you are and where you are going does not shrink in a linear way. It shrinks in a way that reveals just how far the ceiling is from anything you have yet achieved. The speed of light is approximately 670 million miles per hour. The Parker Solar Probe, our fastest achievement, travels at 430,000 miles per hour. That means our fastest spacecraft moves at about 0.064% of the speed of light, not 64%, not 6.4%, 0.064%. We are not close to the speed of light. We are not even in any meaningful physical sense in the same conversation as the speed of light, not yet. The universe has set a speed limit, and we are currently driving at the equivalent of 0.064% of that limit, while the destination is 4.24 light years away. And yet, and this is what I love about this story, what makes it not a story of failure, but a story of audacity. Humans have not accepted this gap. There are people alive right now, working in laboratories and universities and private research facilities who are designing systems that they believe could propel a spacecraft to 10, 20, even 40% of the speed of light. Not within a distant speculative future, within decades. The approaches they are working on are not the rockets you learned about in school. They do not burn fuel in the conventional sense. Some of them do not carry fuel at all. And when we examine them carefully in the section just ahead, we will find something remarkable, not just about engineering, but about what happens to time itself when you start moving fast enough. Because one of the strangest and most beautiful gifts that high speed offers is not just shorter travel time. It is something far more personal, far more strange, far more deeply human than any rocket equation has a right to be. Einstein knew about it. He wrote about it in 1905 in a paper that changed physics forever. And when we finally fold it into our calculation, when we ask not just how long the journey takes in the universe's time, but how long it takes in yours, the answer becomes something that no textbook prepared you for. Einstein wrote it down in 1905. He was 26 years old, working as a patent clerk in Bern, Switzerland, reviewing other people's inventions by day and rewriting the laws of the universe by night. He had no laboratory, no research assistant, no university position, just a desk of mind that refused to stop asking uncomfortable questions and a piece of paper. What he wrote that year in a paper so short it could be read in an afternoon contained an idea so strange that even today, more than a century later, it still feels like it should not be true. It feels like a trick, like a loophole someone found in the rules of reality and has not yet been forced to close. The idea is this time is not fixed. Time is not the same for everyone. Time bends, time stretches. And the faster you move through space, the slower time moves for you, relative to someone who is standing still. This is not a metaphor. This is not a philosophical position. This is a measured, verified, experimentally confirmed fact about the physical universe we live in. And when we fold it into the question of crossing a light year, something happens to the answer that no amount of rocket engineering alone could achieve. The journey that takes 1,550 years at the speed of the Parker Solar Probe, that same journey at high enough velocity, could take a human traveler not centuries, but years, perhaps even months. From the outside, the universe ages by centuries. From the inside of the ship, the traveler barely ages at all. Let that sit for a moment, because we are about to go somewhere very strange and very beautiful. And I want you to be ready. Let us begin with the idea itself, stripped as clean as possible of mathematics, because the mathematics comes later and the idea comes first. Imagine two twins. Call them Anna and Ben. On their 30th birthday, Anna boards a spacecraft capable of traveling at a significant fraction of the speed of light. Ben stays on Earth. Anna waves goodbye, the ship accelerates, and she begins her journey toward a distant star. From Ben's perspective on Earth, Anna's ship is moving very fast. He watches it recede. He goes about his life. Years pass, decades pass. Eventually, let us say, after what Ben experiences as 60 years, Anna's ship returns and lands. Ben, now 90 years old, walks slowly to the landing pad, perhaps leaning on a cane. Anna steps out. She is 35. She has aged 5 years. Her brother has aged 60. They were born on the same day. They are now separated by 55 years of biological aging, despite having started at exactly the same moment. This is not science fiction. This is special relativity. This is what Einstein's equations predict and what experiments have confirmed, not with astronauts and distant stars, but with atomic clocks and aircraft and particle accelerators thousands of times over with extraordinary precision. The first experimental confirmation that time dilation is real came in 1971 in an experiment called the Hoeffel-Keating experiment. Two physicists, Joseph Hoeffele and Richard Keating, flew extremely precise atomic clocks around the world on commercial airliners eastward and then westward, and compared those clocks to identical clocks that had stayed on the ground. The flying clocks having moved faster than the ground clocks, and having been at different altitudes, which introduces a separate gravitational effect, we will come to in a moment, showed measurable differences in elapsed time when they returned. The differences were tiny nanoseconds, billionths of a second, but they matched Einstein's predictions with remarkable accuracy. Nanoseconds might not sound dramatic, but consider what that experiment actually demonstrated. Two clocks starting at the same time, traveling different paths through space-time, and arriving back together, having measured genuinely different amounts of elapsed time. Time itself had passed differently for each clock. Not because the clocks were broken, because time is that way. Since then, time dilation has been confirmed in particle accelerators, where subatomic particles traveling near the speed of light survive for far longer than their natural decay time would predict, because from their perspective, much less time has passed. It has been confirmed in GPS satellite systems, which must account for relativistic time dilation in their calculations. To remain accurate without those corrections, GPS systems would drift by miles within a single day. Every time you use navigation on your phone, you are benefiting from Einstein's equations about the elasticity of time. Now, let us bring this back to the light year. Let us do the numbers that most people never reach, because most explanations stop at time dilation exists, without showing you what it actually means for an interstellar traveler. The key quantity in special relativity is something called the Lorentz factor, usually written with the Greek letter gamma. It describes how much time slows down, or equivalently how much distances contract for a moving observer relative to a stationary one. The formula involves the ratio of the traveler's speed to the speed of light, and it behaves in a fascinating way. It changes very slowly at low speeds, then accelerates dramatically as you approach the speed of light. At 10% of the speed of light, about 67 million miles per hour, far beyond anything we have currently built, the Lorentz factor is approximately 1.005. Time passes about 0.5% slower for the traveler, barely noticeable. At 50% of the speed of light, the Lorentz factor is about 1.15. Time passes about 15% slower, starting to become significant. At 90% of the speed of light, the Lorentz factor is about 2.3. Time passes more than twice as slowly for the traveler. A journey that takes 4.24 years from Earth's perspective would feel like less than 2 years to the traveler. At 99% of the speed of light, the Lorentz factor is approximately 7. That same 4.24 light-year journey takes 4. 24 years as measured from Earth, but the traveler experience is only about 7 months. At 99.9% of the speed of light, the Lorentz factor rises to about 22. The traveler ages less than 2.5 months, while crossing more than 4 light-years of space. At 99.99%, the factor reaches about 70. The journey that takes 4.24 years outside takes the traveler less than 3 weeks. The closer you get to the speed of light, the more dramatically time compresses for the traveler. In principle, not in current engineering practice, but in principle within the laws of physics as we understand them, a human traveler at sufficiently high velocity could cross a light year and experience only days of subjective time, while years or decades pass outside. Here is the common mistake I want to address because it trips up even careful thinkers. Many people, when they first encounter time dilation, assume it means you can cheat the light year, that if time slows down enough, you can effectively travel faster than light from your own subjective perspective. And in a narrow sense, that impression is correct. A traveler moving at 99.99% of the speed of light does cover enormous distances in very little personal time. But here is what the physics also says. With equal clarity, you never actually travel faster than light. From any external observer's perspective, you are always moving slower than light. The universe as seen from outside your ship still takes exactly as long as light travel time requires. The star you are heading toward still receives your arrival signal only after you have been there for however long it takes light to catch up. Time dilation does not break the light speed limit. It is not a loophole. It is instead something more interesting, a gift the universe offers to the traveler, specifically at the cost of a strange disconnection from everyone they left behind. The traveler ages slowly, the universe does not. They arrive young at their destination, but everyone who waved goodbye has aged by the full travel time. If you travel to a star 10 light years away at 99.99% of light speed, you might experience the journey as a few weeks. But 10 years have passed on Earth. You cannot have it both ways. The universe is extraordinarily precise about this. This is the heart of what physicists call the twin paradox, which is not actually a paradox at all. It just feels like one until you work through the geometry of it. The twins do not age at the same rate. The one who traveled genuinely, measurably, physically ages less. They are not the same age when they meet again. They never will be. There is a human dimension to this that I find almost unbearably poignant, and I want to stay with it for a moment rather than rushing past it toward the next equation. Imagine you were the traveler. You leave Earth at age 30. You travel at 99% of light speed to a star 12 light years away, spend a few months exploring and return. The round trip takes, from your perspective, perhaps 3 years. You arrive back at age 33. On Earth, 24 years have passed. Your parents, who were in their 60s when you left, are now in their mid-80s if they are still alive. Your friends have built careers, raised children, buried other friends. The world has changed in ways you did not witness and cannot fully absorb. The music has changed. The slang has changed. The political landscape is unrecognizable. People you loved have moved on, not because they chose to, but because time moved on and they moved with it as time requires. You step off the ship and you are 33 and the world you knew is gone. This is not a technological problem. There is no engineering solution to it. It is built into the structure of space-time itself. The universe does not allow you to have. Both you cannot travel fast enough to experience the journey in a human-scale time frame and also return to the world you left intact. Choose one. The physics will not negotiate. I think about the explorers of the Age of Sail, the ones who left European ports in the 15th and 16th centuries on voyages that took years, who returned to find that people had died in their absence, that children they had said goodbye to were now adults, that the world had quietly continued without them. They understood something in a visceral and practical way about the cost of distance, about the price of going far. Interstellar travel would simply make that cost absolute, irreversible, measured not in months, but in years or decades of subjective separation from every human connection you carried onto the ship. And there is one more layer to this that Einstein gave us, which goes beyond special relativity into general relativity. The theory he completed 10 years later, in 1915, which extended his ideas from constant speed motion to accelerating motion and gravity. General relativity adds something crucial. Gravity also bends time, not just speed. Gravity. The stronger the gravitational field, the slower time runs. A clock on the surface of the Earth runs very slightly slower than a clock in orbit because Earth's gravity is pulling on it. A clock near a black hole, where gravity becomes so intense that not even light can escape, would run almost infinitely slowly relative to a clock far away. This means that the hypothetical traveler's experience is shaped not just by how fast they move, but by every gravitational field they pass through. A close flyby of a massive star would add gravitational time dilation on top of velocity time dilation. In principle, a skilled navigator with sufficient technology could use the combined effects, high velocity and strategic gravitational encounters, to compress subjective travel time even further than either effect alone would allow. The universe is in a sense full of natural time machines. Not machines that go backward, nothing in known physics permits that, but forward-leaning time machines, natural features of space-time that allow certain travelers to arrive at the future sooner than others, having aged less along the way. Black holes are the most extreme version. Research suggests that if you orbited sufficiently close to a stellar mass black hole for what felt to you like an hour years might pass for the rest of the universe. This is not a thought experiment. This is a prediction of general relativity that has been tested and confirmed in every way available to us, short of actually orbiting a black hole. The physics is solid. Here is what I want you to take from all of this as a single coherent thought before we move forward. We have established that crossing a light year is at human walking pace a 192 million year project. We have established that even our fastest spacecraft reduces that to about 1,550 years. And now we have established that the physics of relativity offers something extraordinary at sufficiently high velocities. A human being could experience a light-year crossing in a subjective time frame, measured not in centuries, but in years, perhaps even months. The barrier is not time. The barrier is not physics. The barrier, the real practical engineering barrier, is energy. To accelerate a spacecraft to 90% of the speed of light requires an amount of energy that dwarfs anything we have ever generated. To reach 99% requires more still. To reach 99.9%, where the time compression becomes truly dramatic, requires energy on a scale that makes our current best rocket engines look like candles beside a supernova. And this is where the story turns toward the dreamers, the people who looked at that energy requirement and did not say impossible, who said instead, what if we found a different source? What if the energy was already out there waiting in the form of light itself, streaming endlessly from every star in the galaxy? What if the ship did not need to carry its fuel at all? That question is where the next part of this journey begins in the minds of people who dreamed of sails made not of canvas but of light and ships that weigh no more than a few grams, and laser arrays that could push them to the stars within a human lifetime. So, the physics says it is possible, not easy, not imminent, but possible within the laws of the universe as we understand them. A human being moving fast enough could cross a light year and experience it in a compressed personal time frame. The equations permit it. The universe does not forbid it. But the universe does not build the ship. We do. And the ship must carry something the equations tend to leave out of their elegant notation. Something inconvenient, fragile, and absolutely non-negotiable. A human body, not a point mass, not a theoretical traveler. A body with lungs that need air at precise pressures, with bones that dissolve quietly in the absence of gravity, with a cardiovascular system that was designed over millions of years of evolution, specifically for the conditions of one particular planet, at one particular distance from one particular star. A body that gets lonely, that needs sleep, that carries somewhere in its chest the persistent and irrational need to belong somewhere. The physics of interstellar travel is extraordinary. The biology of it is in many ways even more challenging. And tonight that is what we are going to look at. Not the equations, but the flesh. Not the theory, but the cost. Let us begin with something that most people do not think about when they imagine space travel, because science fiction has largely edited it out of the picture: radiation. Here on Earth, we are protected from the worst of space radiation by two overlapping shields. The first is the magnetosphere, the invisible magnetic bubble generated by Earth's iron core, which deflects the charged particles streaming from the sun and from distant cosmic sources, bending them away from the surface the way a curved windshield deflects rain. The The second is the atmosphere's 60 miles of air above your head, dense enough to absorb much of what the magnetosphere does not deflect. Together, these two shields reduce the radiation reaching your body to a level low enough that you can live a full lifetime without significant radiation-induced illness, assuming you avoid unnecessary medical X-rays and do not spend too much time in high-altitude regions where the atmospheric shield is thinner. Outside those shields in deep space beyond Earth's magnetosphere and far above its atmosphere, there are two main radiation threats, and both are serious. The first is solar energetic particles, bursts of high-energy protons and electrons ejected by the sun during solar flares and coronal mass ejections. These events can release more energy in a few hours than the sun normally emits in years, and the particles they fling outward are moving fast enough to penetrate all but the most substantial shielding. A major solar energetic particle event in deep space without adequate protection could deliver a lethal radiation dose in hours. The second, and in some ways more insidious threat, is galactic cosmic rays, high-energy particles, some of them protons, some of them heavy atomic nuclei, accelerated to near-light speeds by supernovae and other violent processes elsewhere in the galaxy. These particles arrive from all directions continuously, and they are so energetic that they pass through most practical shielding materials with ease. You cannot simply add more metal and solve the problem. Thick metal shielding can actually make galactic cosmic ray exposure worse because when these particles strike the hull, they produce secondary radiation, a spray of smaller particles released by the impact, creating a halo of additional exposure around the shielding itself. Research from the ISS and from studies of Apollo astronauts suggests that even at relatively short distances from Earth, radiation exposure begins accumulating in ways that increase long-term cancer risk, cause subtle damage to the central nervous system, and may affect cognition, memory, and emotional regulation. Astronauts who have spent extended time in space report seeing flashes of light with their eyes closed, not a visual illusion, but actual cosmic ray particles passing through the fluid of their eyeballs and triggering the optic nerve directly. Think about that for a moment. Light that does not exist seen by a brain that knows it is in the dark, caused by a particle that traveled across half the galaxy to pass through a human eye at precisely that moment. The universe announcing itself privately to one person at a time. Now, let us talk about bones. The human skeleton was not designed to last. It was designed to be used to be loaded, stressed, compressed, and bent by the constant pull of gravity that has shaped every land animal on Earth for hundreds of millions of years. Bone is living tissue. It is continuously broken down and rebuilt by specialized cells, and the primary signal that triggers rebuilding is mechanical stress. Load a bone, and it signals its cells to maintain density. Remove the load, and the signal weakens, and the cells that break bone down become more active than the cells that build it up. In microgravity, the near weightlessness of an orbiting spacecraft, this process accelerates in a deeply unwelcome direction. Astronauts on the International Space Station, which orbits at a relatively modest altitude and has a well-developed exercise protocol, specifically designed to combat this, still lose approximately 1 to 2% of bone density per month in weight-bearing bones, like the hips and spine, per month. For a 6-month mission, a standard ISS rotation that represents a significant loss that requires months of rehabilitation on return. For longer missions, the trajectory of bone loss, if not fully arrested by exercise, could eventually compromise structural integrity. Bones that were designed to carry a body through a lifetime of standing and walking could become brittle enough to fracture under ordinary loads. The muscle system faces the same problem. Without gravity to work against muscles, atrophy with remarkable speed. Astronauts on the ISS exercise 2 hours every day, not for fitness in any conventional sense, but simply to slow the rate at which their bodies are consuming themselves. And even with 2 hours of daily exercise, significant muscle loss still occurs over a 6-month stay. Now think about a journey measured not in months, but in years, or decades, or generations. There is a question hiding in those numbers that I want to ask you directly. If you were told that a journey to the nearest star would take in your subjective experience roughly 20 years, and that those 20 years would require extraordinary discipline just to arrive in a condition capable of completing the mission, would you go? Not would you want to go in the abstract dreaming sense, but really go. Leave, board the ship. Watch Earth shrink behind you, knowing that everyone you love is aging faster than you, that the world you knew is changing without you, and that your body is working against you every day, requiring hours of maintenance just to stay functional, I ask. Because the history of exploration suggests that people do say yes to exactly these kinds of bargains. They always have. The crews of the Great Pacific Voyaging canoes, the Polynesian navigators who crossed thousands of miles of open ocean to settle Hawaii and New Zealand and Easter Island in boats with no instruments beyond their knowledge of stars and waves and birds, they said yes to a version of this. They left everything they knew, pointed their prows at the horizon, and did not turn back. What they carried was not certainty. It was something quieter, something closer to faith in the worthiness of the question. Let us go deeper into the biological challenges, because there is one that most popular science coverage barely mentions, and I think it may be the most significant of all: the human immune system. Research from ISS crews and from ground-based simulated isolation studies has revealed something unexpected and genuinely concerning. In space, the immune system does not simply weaken in a general way. It behaves strangely, erratically. Some immune functions are suppressed. The body becomes more susceptible to viral infections, and dormant viruses, like the Epstein-Barr virus, which causes mononucleosis, and the varicella-zoster virus, which causes chickenpox and shingles, have been observed to reactivate in astronauts in space, waking up after years of dormancy, as though the immune system that had been keeping them quiet lost its grip. At the same time, other immune functions become overactivated. Inflammatory markers increase. The balance that defines a healthy immune response, the careful calibration between response and restraint, shifts in ways that are still not fully understood and that likely have long-term health consequences we have not yet had long enough exposure to fully map. The suspected culprit, or at least one major contributor, is stress. Not emotional stress alone, though that is real, but the combined physiological stress of radiation, disrupted circadian rhythms, altered sleep, architecture, changed gut microbiome, composition, due to the space diet and environment, and the constant low-level demand of living in a machine that requires vigilance to survive. Space, in other words, is not just physically challenging. It is physiologically depleting in ways that compound over time, accumulating like interest on a debt that cannot be fully repaid by exercise or medication or any intervention currently known. And then there is the mind. In 2010 and 2011, a simulation called Mars 500 was conducted in Moscow. 6 volunteer crew members sealed themselves inside a mock spacecraft for 520 days, the estimated round-trip duration of a Mars mission, without leaving without real-time communication with the outside world, living on mission-style rations and following a structured daily schedule. No actual space travel, just the isolation and confinement replicated as faithfully as possible on the ground. The results were illuminating and sobering. Over the course of 520 days, the crew members' sleep patterns became increasingly disrupted. Their activity levels dropped significantly, not because the schedule changed, but because their brains and bodies gradually quietly withdrew. Several crew members developed what researchers described as psychological hibernation, a state of increasing disengagement, reduced motivation, and emotional flattening that the subjects themselves did not always consciously recognize because it crept in so slowly. None of them were in space. None of them were exposed to radiation or microgravity. They were in Moscow in a building with trained psychologists monitoring them. And still, after 520 days of confinement and isolation, the cognitive and psychological toll was measurable and significant. Now, scale that to an interstellar journey, not 520 days, but years, potentially decades. In a vessel where the view from every window is identical, an absolute featureless blackness, punctuated by stars that do not visibly change position from month to month, because you are still too far away from anything for parallax to show. A darkness so complete and uniform that the human visual system, which evolved to track movement and change as signals of importance, finds almost nothing to anchor to. Research on Antarctic winter-over personnel. Scientists who spend months at polar research stations during the total darkness of Antarctic winter, effectively isolated from the rest of humanity, has documented a cluster of symptoms sometimes called the winter-over syndrome: mild cognitive impairment, memory problems, difficulty concentrating, irritability, and a peculiar perceptual distortion, where the sense of time becomes unreliable. Days feel indistinguishable. The normal markers that structure a human week, the varied light, the social rhythms, the sensory variety disappear, and without them, the mind begins to lose its grip on ordinary temporal orientation. In Antarctic stations, there is still gravity. There is still a ground and a sky, even if the sky is dark. There is still wind and temperature change, and the physical sensation of a planet beneath your feet. None of those things exist on an interstellar spacecraft. The sensory impoverishment of deep space travel would be more complete than anything a polar station can simulate. Here is what I find most interesting about all of this. The thing that makes the biology not just a list of obstacles, but a genuine philosophical puzzle. Every single one of these problems, the radiation, the bone loss, the immune dysregulation, the psychological hibernation, is a problem precisely because the human body is so extraordinarily well adapted to Earth. These are not design flaws. They are design features that happen to be catastrophically mismatched to the environment of interstellar space. The bone loss happens because bones were brilliantly optimized for a one-gravity world. The immune strangeness happens because the immune system was exquisitely calibrated for the microbial landscape of Earth over millions of years of evolution. The psychological hibernation happens because human consciousness was shaped by an environment of constant sensory variation. Seasons, sunrises, the movement of animals, the unpredictability of weather. And when that variation is removed, the mind does not know what to do with the silence. We are in the most literal biological sense creatures of this planet, not in a poetic way, in a cellular, molecular, neurological way. Every system in the body carries the imprint of Earth, its gravity, its light cycle, its magnetic field, its particular mix of atmospheric gases, its temperature range, its microbial diversity. To leave Earth for long enough and far enough is not just a logistical challenge. It is in a sense an act of profound biological exile. The body knows where it belongs. And in the silence between stars, it whispers that knowledge in ways we are only beginning to understand. The scientists and engineers who take these challenges seriously, and there are many who do in labs at NASA, ESA, and universities around the world, have begun to think about solutions that go far beyond exercise machines and vitamin supplements. They are thinking about biology itself as a design problem, about whether the human body, given enough time and enough biotechnology, could be modified gradually, carefully, ethically to handle what space requires. But there is another approach, one that does not modify the traveler, but instead removes the traveler from the experience of the journey entirely, one that has been seriously studied, carefully modeled, and partially tested in the laboratory. An approach borrowed not from engineering, but from nature, from the bears and ground squirrels and Arctic frogs that every winter perform a small miracle so ordinary we barely notice it. They go to sleep, and when they wake up, the cold is over. What that means for interstellar travel, how close the science actually is, and what it would cost to step into that sleep. Knowing the world you left, will be unrecognizable when you open your eyes. That is exactly where we are headed next. There is a ground squirrel in the Arctic, a small, unremarkable-looking creature called the Arctic ground squirrel, Urositellus perii, that does something every autumn that no human engineer has yet been able to fully replicate in a laboratory. It finds a burrow, it curls into a ball, and it lowers its body temperature to just below the freezing point of water, as low as -3 degrees Celsius, colder than any other warm-blooded mammal is known to survive, and it stays there for 8 months, not sleeping in the way you are, perhaps drifting toward right now, with your breathing steady and your heart beating and your brain cycling through its quiet dreams. But something far deeper, something that biologists call torpor, and that the rest of us, reaching for the right word, tend to call suspended animation. Its heart rate drops from a normal 200 beats per minute to about 3 beats per minute. Its metabolism slows to less than 1% of its waking rate. Its brain activity flattens to near nothing. For 8 months, it consumes almost no energy, produces almost no waste, and ages at a rate so slow it is barely measurable. And then in spring, it wakes up. Its heart accelerates. Its temperature climbs. It uncurls, blinks at the light, and walks out into an Arctic morning, as though no time has passed at all. If we could do that, if a human being could be placed into genuine metabolic hibernation for the duration of an interstellar journey, almost every biological problem we discussed in the previous section would dissolve. The radiation exposure would accumulate more slowly in a body with a minimal metabolic rate. The bone loss and muscle atrophy would slow dramatically. The psychological toll of isolation and confinement would simply not exist because there would be no consciousness to experience the passing years. You would close your eyes on Earth and open them at the stars. The question is not whether we want this. The question is whether the biology will let us have it. Let us begin with what we know not from science fiction, but from the actual science of torpor and hibernation, which is richer and stranger than most people realize. True hibernation, the kind the Arctic ground squirrel performs, is not simply deep sleep. It is a fundamentally different physiological state, involving a coordinated suppression of nearly every metabolic process in the body. And crucially, it appears to be actively regulated. The animal is not passively cooling down the way a stone cools when you take it out of the sun. It is actively managing a controlled metabolic shutdown, guided by biochemical signals that researchers are still working to fully understand. One of the key molecules involved appears to be hydrogen sulfide, yes, the same compound responsible for the smell of rotten eggs, which at extremely low concentrations has been shown to induce a torpor-like state in mice in laboratory settings. In 2005, a team at the Fred Hutchinson Cancer Research Center in Seattle published a landmark paper showing that mice exposed to 80 parts per million of hydrogen sulfide in their breathing air reduced their oxygen consumption by up to 90% and dropped their core body temperature to near ambient levels. When the hydrogen sulfide was removed, the mice returned to normal function without apparent harm. Mice are not ground squirrels. And ground squirrels are not humans. But the existence of this pathway, a biochemical switch that can dial down metabolism dramatically, suggests that the machinery for torpor may be present in mammalian biology broadly, including in humans, even if it is not normally activated. Evolution may have conserved the mechanism across mammalian lineages, even in species that do not naturally hibernate. This is the theoretical foundation on which the science of induced human hibernation currently rests. Not certainty. Not a working prototype, but a genuine biological plausibility that serious scientists take seriously. The medical world has already taken the first tentative steps in this direction, though under a different name and for a different purpose: therapeutic hypothermia. The deliberate cooling of a patient's body temperature to reduce metabolic demand during a medical crisis is now standard practice in certain emergency and surgical settings. Cardiac surgery is sometimes performed with the patient cooled to around 18 degrees Celsius. Their hearts stop their circulation maintained by a bypass machine, their brain protected from damage by the reduced metabolic rate. The surgeon has, in effect, temporarily suspended the patient's biology to create a still, quiet field in which to work. In trauma medicine, a procedure called emergency preservation and resuscitation, developed at the University of Pittsburgh under the direction of Dr. Samuel Tischerman, has been used in experimental settings to cool patients who have suffered catastrophic blood loss to around 10 degrees Celsius, buying time for surgical repair that would be impossible in a normally metabolizing body. At that temperature, brain activity is nearly absent, and oxygen consumption is reduced by approximately 90%. The patient is for a brief window in a state that lies on the spectrum toward what the Arctic ground squirrel experiences for 8 months every year. The patients in these procedures are not in hibernation in the full biological sense. They are cooled externally, not through the internal biochemical cascade that regulates true torpor. And the procedures currently last hours, not months. But the principle that a human body can be substantially slowed down without being destroyed has been demonstrated in clinical reality, not just laboratory mice. The gap between cooled for 4 hours during surgery and maintained in metabolic suspension for 20 years during interstellar transit is enormous, but it is not infinite, and the direction of travel is clear. Now, let us turn to the second great dream of interstellar engineering, one that approaches the problem from the opposite direction, not slowing the traveler down, but making the ship so fast that the traveler barely has time to miss anything. In 2016, a project called Breakthrough Starshot was announced, backed by physicist Stephen Hawking, technology investor Yuri Milner, and a coalition of scientists and engineers who had in various ways spent their careers thinking about the hardest problems in physics. The proposal was audacious to the point of seeming at first glance like something a child might dream up, and an adult would immediately dismiss. The plan built a fleet of spacecraft, not the kind of spacecraft you are picturing, not a vessel with rooms and corridors and life support systems and crew quarters, a spacecraft the size of a postage stamp, a chip essentially a few grams of silicon carrying cameras, sensors, a power source, and a laser communication system, attached to a sail made of material so thin that it is measured in nanometers. The entire system sail, and all weighing perhaps a gram or two, then build an array of ground-based lasers, a phased array with a combined output of roughly 100 gigawatts, which is approximately the total electrical generating capacity of all the nuclear power plants in the United States, focused into a single coherent beam, and fire that beam at the sail for a few minutes. The light from the laser pushes against the sail. Light carries momentum, a fact confirmed by James Clerk Maxwell's equations in the 1860s, and experimentally verified since and when enough of it strikes a sufficiently light surface, it pushes. Not hard enough to matter for anything with significant mass, but for a 1-gram spacecraft, 100 gigawatts of laser light pushing for 2 minutes could theoretically accelerate it to approximately 20% of the speed of light. At 20% of the speed of light, the journey to Proxima Centauri takes about 20 years, a human lifetime, not an eternity, not a geological epoch. 20 years the time between a child's birth and their first years of adult independence. The postage stamp spacecraft would arrive at Proxima Centauri in 20 years, photograph whatever it found, and begin transmitting the data home. That transmission, traveling at the speed of light, would take another 4.24 years to arrive. So, roughly 24 years after launch, humanity could in principle receive the first close-up images of another star system. There is a common and entirely understandable objection to Breakthrough Starshot, and I want to address it directly because it reveals something important about how we evaluate ambitious ideas. The objection is, the engineering is impossible. 100 gigawatts of focused laser power does not exist. The sail material thin enough to be accelerated by light pressure, strong enough to survive the acceleration, and able to handle the thermal load of 100 gigawatts of laser energy without vaporizing does not currently exist. The pointing accuracy required to keep a laser focused on a gram-scale sail, accelerating away at a fraction of the speed of light over a distance of millions of miles, exceeds anything currently demonstrated. The miniaturized spacecraft carrying functional cameras and a laser transceiver in a package weighing about a gram is beyond current fabrication capability. All of that is true, every word of it. But here is what is also true: in 1903, control-powered flight did not exist. The Wright brothers flew at Kitty Hawk in December of that year, covering 120 feet in 12 seconds. 66 years later, humans walked on the moon. The distance between 12 seconds of powered flight and footprints on another world was covered in a single human lifetime. The history of technology is not a smooth curve. It is a series of long plateaus interrupted by sudden, almost violent leaps that redefine what the word possible means. The laser was invented in 1960. The integrated circuit was invented in 1958. The miniaturization of electronics has followed a trajectory that even 50 years ago would have seemed like fantasy. The engineers working on Breakthrough Starshot are not claiming they can build it today. They are claiming that the physics permits it, and that the engineering challenges, while formidable, are of the kind that human ingenuity, given sufficient time and investment, has historically found ways to solve. Let us come back to the human question. Because Breakthrough Starshot, brilliant as it is, sends a chip, not a person. And the dream that lives at the center of this whole conversation is not about sending cameras to another star. It is about sending us. This is where the concept of the generation ship enters the grandest, most ancient, and, in some ways, most deeply human of all interstellar travel proposals. Not a ship that goes fast, not a ship that puts its crew to sleep, but a ship that simply goes slowly and steadily, carrying within it not just the first crew, but all the generations that will follow a traveling civilization, a world in miniature pointed at a star. The idea has roots that go back further than rockets. The mathematician Konstantin Tsiolkovsky, often called the father of astronautics, a Russian schoolteacher who worked out the fundamental equations of rocket propulsion in the 1890s, decades before anyone had built a working rocket, proposed the concept of a Noah's Ark in space in 1928, a self-sustaining vessel carrying a human community through the void, generation after generation, arriving at another star long after everyone who boarded had died and been succeeded by their children's children's children. The physicist J.D. Bernal elaborated on this in 1929 in a remarkable book called The World, the Flesh, and the Devil, in which he described what he called a Bernal sphere, a rotating hollow sphere several miles in diameter, carrying a population of thousands of people, with the interior surface lined with soil and water and light, simulating gravity through rotation, a miniature Earth traveling between the stars. These ideas were visionary and vague in equal measure, but they planted something in the scientific imagination that has never quite left the notion that interstellar travel might not require us to be faster than we are, or to sleep away the journey, or to send only machines. It might simply require us to be willing to begin something we will not finish. To take the first step of a walk our descendants will complete. Here is what I find most quietly moving about the generation ship concept. And I want you to sit with this, because I think it says something true about the human condition that goes beyond astronomy. A generation ship crew would live their entire lives in transit. They would be born in space, grow up in space, fall in love in space, raise children in space, and die in space, all without ever seeing the destination. The star they were heading toward would be a point of light in a window slightly brighter than the others, growing imperceptibly over decades. They would never arrive. Their children might not arrive. It would be their grandchildren or great-grandchildren or some generation so far removed from the founders that the founders exist only as names in a ship's log who would finally decelerate and enter the gravity well of another sun. What would it mean to live a full, meaningful human life in service of a destination you would never reach? What would the founders say to the children they raised in that ship, knowing they were sentencing them to a life between worlds? And here is the turn. Is that so different from what we already do? Every generation of humans has lived within a project, begun by ancestors and not yet completed. Every person alive today is benefiting from institutions, infrastructures, and accumulated knowledge built by people who died before they could see the results. The medieval stonemasons who laid the foundations of cathedrals that took 2 centuries to complete knew they would not see the spires. The scientists who first identified the structure of DNA in 1953 could not have imagined the gene therapies being developed in their honor today. Every generation is, in a sense, a crew in transit living fully in the journey, building toward a destination that belongs to those who come after. The generation ship is not as alien to human experience as it first appears. It is in some ways simply an honest description of what it has always meant to be human. And then there is the question of what you bring, not fuel, not spare parts, but culture, memory, the things that make a group of people more than a biological population and closer to a civilization. The designers of real-world generation ship proposals, and there are serious academic papers on this from researchers at places like NASA's Ames Research Center and the Initiative for Interstellar Studies in the UK, have grappled with this question in extraordinary detail. How large does a founding population need to be to maintain sufficient genetic diversity over many generations without inbreeding depression? The answer, based on population genetics modeling, is somewhere between 14,000 and 40,000 individuals, far larger than most early science fiction imagined, and large enough that the ship itself would need to be something closer to a small city than a spacecraft. What governance structure would prevent the kind of social fragmentation and conflict that history suggests is inevitable when any large group of people is confined for extended periods? How do you maintain the mission across generations, ensuring that descendants honor the commitment made by ancestors they never knew? How do you preserve the knowledge and motivation to decelerate the ship at journey's end? A technical maneuver requiring precise execution, when the people who must perform it were born knowing nothing but the interior of the ship, and may in some psychological sense have no concept of arrival as a real thing that will happen to them personally. These are not engineering questions. They are questions about human nature, social cohesion, memory, and meaning. And the fact that serious scientists are asking them that these papers exist, that these conferences happen, tells us something important. The dream of interstellar travel is no longer purely the domain of dreamers. It has become, in its own quiet way, a field of study, a discipline, a form of preparation. We are preparing for something we cannot yet do. We are designing solutions to problems we have not yet encountered. We are writing the operational manuals for ships that have not been built to carry people who have not been born to stars we have not yet visited. That is an unusual thing for a species to do. It implies a relationship with the future that is less about certainty and more about commitment, less about knowing you will succeed and more about deciding that the question is worth the trying. And the trying has already begun, not with ships, but with lenses, with mirrors, with instruments of extraordinary sensitivity pointed at a small red star, 4.24 light-years away, looking for something that would change everything, looking for a world that might be waiting, a world that might already have weather and seasons and perhaps something stirring in its ancient light. What the telescopes have found at Proxima Centauri and what it means for every calculation we have made tonight is exactly where this journey leads next. On the night of January 16, 2016, an astronomer named Guillem Anglada Escudé sat in his office at Queen Mary University of London and looked at a data set that had been quietly accumulating for years, a long series of measurements of a small, dim red star called Proxima Centauri, gathered by telescopes in Chile using a technique called the radial velocity method, which detects the tiny wobble a planet's gravity induces in its parent star as it orbits. The signal was there, faint but consistent, repeating with a period of 11.2 days. A planet. A planet orbiting Proxima Centauri in its habitable zone, the region where liquid water could theoretically exist on a rocky surface at a distance from its star that receives roughly 65% of the energy Earth receives from the Sun. When the paper was published in Nature in August 2016, the scientific community responded with a mixture of excitement and careful restraint. That is in its own way one of the most human reactions in science. We want this to be what it looks like, and we are terrified of being wrong. The planet was named Proxima b, and its existence transformed the question we have been asking all night from a purely theoretical exercise into something with a possible address. The nearest star to our Sun, 4.24 light-years away. The destination of every calculation we have made tonight may have a world orbiting it, a rocky world, a world that sits in the zone where life as we know it does not become thermodynamically impossible. Everything we have discussed, the walking times, the relativistic clocks, the generation, ships, the laser sails, all of it, now has a potential destination with a name. And the story of what we have found there and what we do not yet know, and what the James Webb Space Telescope is beginning to reveal about worlds like it is, where this part of the journey takes us. Let us understand what the radial velocity method actually measures, because it is elegant in a way that rewards attention. When a planet orbits a star, it does not simply circle around a stationary point. Both the star and the planet orbit their common center of mass, the balancing point of the system weighted by the relative masses of the two objects. Because stars are vastly more massive than their planets, this center of mass is usually very close to, or even inside, the star itself. But it is not exactly at the star's center, and so the star wobbles ever so slightly, pulled first toward the planet and then away from it as the planet completes each orbit. This wobble is tiny. For a planet the size of Earth orbiting a star the size of the Sun, the induced wobble is about 9 centimeters per second, roughly the walking speed of a tortoise. Measuring that from light years away requires spectroscopes of extraordinary sensitivity, capable of detecting shifts in starlight caused by Doppler effect, the same principle that makes an ambulance siren pitch up as it approaches you and pitch down as it recedes, but applied to light waves rather than sound waves. When a star moves toward us, even by centimeters per second, its light is compressed very slightly toward the blue end of the spectrum. When it moves away, the light stretches slightly toward the red. By measuring these shifts in the spectral lines of starlight with sufficient precision, astronomers can infer the presence of orbiting planets without ever directly seeing them. It is in a sense hearing a planet rather than seeing it, detecting its gravitational voice in the light of its parent star from 25 trillion miles away. By measuring color shifts smaller than the width of a single atom in a spectrum. The fact that this works, that this is real operational science producing confirmed results, is one of the quiet miracles of contemporary astronomy. Now let us talk about what we actually know about Proxima b. And this is equally important, what we do not know, because the gap between those two things is where the most interesting science currently lives. What we know, Proxima b has a mass at least 1.07 times that of Earth. It could be larger, depending on the orientation of its orbit relative to our line of sight, which affects how we interpret the radial velocity signal. It orbits Proxima Centauri at a distance of about 6 million miles, much closer than Earth, orbits the Sun. But Proxima Centauri is a red dwarf star, much cooler and dimmer than the Sun. So that close distance still places the planet within the habitable zone as astronomers define it. Its orbital period is 11.2 days. If you lived on Proxima b, if such a thing were possible, a year would be 11 days long. The star in your sky would appear roughly 3 times larger than our sun, appears in ours glowing in a deep reddish orange rather than the yellow-white of our daylight. What we do not know almost everything else. We do not know if Proxima b has an atmosphere. We do not know if it has liquid water. We do not know its surface temperature with confidence. We do not know if it is a rocky world like Earth, or a water world entirely covered in ocean or a barren airless rock. We do not know if it is tidally locked, which is likely given its proximity to its star, meaning one hemisphere may perpetually face the star in eternal noon, while the other faces the cold, dark and eternal midnight, with a thin twilight belt between them, where conditions might be most Earth-like. And we do not know, we simply honestly do not know, whether anything lives there. Here is a misconception I want to address directly, because it surfaces in almost every popular discussion of habitable zone exoplanets, and it quietly distorts how people think about the search for life. The misconception is this: a planet in the habitable zone is likely to be habitable. The habitable zone is defined purely in terms of energy flux, the amount of stellar radiation the planet receives that could in principle allow liquid water to exist on its surface if it has the right atmospheric conditions. That is all the habitable zone means. It is not a prediction of habitability. It is a necessary but far from sufficient condition. Venus orbits within the Sun's habitable zone. Venus has a surface temperature of 465 degrees Celsius, a crushing atmosphere of carbon dioxide, sulfuric acid clouds, and atmospheric pressure, 90 times that of Earth. Venus is the least habitable place in the inner solar system, and it sits in the habitable zone. Mars also sits within or very close to the outer edge of the habitable zone. Mars has a thin atmosphere, no global magnetic field, and average temperatures of negative 60 degrees Celsius. It may have had liquid water billions of years ago, but today its surface is exposed to intense ultraviolet radiation and is, as far as we know, sterile. For Proxima b, there are additional challenges specific to its situation around a red dwarf. Red dwarf stars, and Proxima Centauri is the most studied example, are known for intense stellar flare activity. Unlike the Sun, which produces major flares relatively infrequently, Proxima Centauri flares regularly and violently, releasing bursts of ultraviolet and X-ray radiation that could, if Proxima b lacks a strong magnetic field and substantial atmosphere, strip away its air over geological timescales. In March 2017, astronomers detected a super flare from Proxima Centauri, approximately 10 times more energetic than the most powerful solar flare ever recorded from our Sun. If Proxima b was bathed in that radiation without protection, the surface dose would have been catastrophic for any biology resembling what we know on Earth. Does this mean Proxima b is definitely lifeless? No. Does it mean the habitable zone designation alone tells us very little? Yes, absolutely. The real question is not, is this planet in the habitable zone, but what kind of world is this specifically? And what does its atmosphere, if it has one, actually do? And that is precisely where the James Webb Space Telescope enters the story. The James Webb Space Telescope launched on Christmas Day 2021 after decades of development, cost overruns, technical challenges, and delays that tested the patience of an entire generation of astronomers. Represents the most powerful observatory humanity has ever placed in space. Its primary mirror, nearly 21 feet in diameter, is made of 18 hexagonal gold-plated beryllium segments that unfold in space like the petals of a flower. It observes primarily in the infrared light with wavelengths longer than what human eyes can see, which allows it to pierce dust. Clouds look back to the earliest galaxies and, crucially for our purposes, analyze the atmospheres of exoplanets in ways no previous telescope could. The technique is called transmission spectroscopy. When an exoplanet passes in front of its star, a transit some of the starlight filters through the edges of the planet's atmosphere, if it has one. Different molecules in that atmosphere absorb different wavelengths of light, leaving characteristic signatures in the transmitted spectrum. By carefully measuring which wavelengths are absorbed and in what proportions astronomers can infer what the atmosphere is made of, whether it contains water, vapor, carbon, dioxide, methane, oxygen, ozone, or other compounds. This is in its way just as elegant as the radial velocity method, a form of remote sensing so delicate it can determine the chemistry of an atmosphere from trillions of miles away, using only the shadows cast by molecules in starlight. Webb has already used this technique to make extraordinary discoveries. In 2023, it detected carbon dioxide, sulfur dioxide, and water vapor in the atmosphere of a planet called WASP, 39 big gas giant, orbiting very close to its star. Not a candidate for life, but a proof of concept that the technique works. In 2024, researchers announced that Webb data from a planet called K218b showed the possible presence of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms, specifically marine phytoplankton. The researchers were careful to note that the detection was tentative and required confirmation, and that non-biological production of dimethyl sulfide in exotic atmospheric chemistry could not be ruled out. But the signal was there, discussed in the most careful scientific language. And the careful scientific language was wrapped around an idea that, if confirmed, would be the most significant discovery in the history of humanity: life elsewhere. Proxima b presents a special challenge for transmission spectroscopy because it does not appear to transit its star from our perspective. Or if it does, the transits have not been confirmed. Without transits, Webb cannot directly sample its atmosphere in the usual way. But alternative observation strategies, direct imaging techniques, reflected light analysis, thermal emission measurements are being actively developed, and the next generation of ground-based telescopes, including the extremely large telescope currently under construction in Chile's Atacama Desert, will have the capability to directly image Proxima b and attempt atmospheric characterization. The extremely large telescope, when completed, will have a primary mirror nearly 130 feet in diameter, larger than the largest optical telescope currently operating by a factor of 5. It will be capable of directly resolving the disk of Proxima b and measuring reflected light from its surface and atmosphere. If there is an atmosphere there, and if it contains the right molecules, we will know within perhaps a decade, 10 years. In the context of the timescales we have been discussing tonight, 192 million years to walk there, 73,000 years for Voyager to reach it. 10 years is an eye blink. It is less than the time between two Olympics. It is possible that a child born today will be a teenager when the first spectroscopic characterization of Proxima b is announced. I want to pause here and ask you something, because I think it is one of the most genuinely interesting questions that emerges from everything we have covered tonight. If we discovered definitively that Proxima b has a biosphere, that life exists there, that the atmospheric chemistry is unmistakably biological, what would that change? Practically not immediately. The planet would still be 4.24 light years away. We would still have no technology to reach it in a human lifetime. We could not go there, not yet, not in any time scale that would feel meaningful to the person receiving the news. But what would it mean? What would it do to the way the 6 or 8 or 10 billion people on Earth at that moment understood their place in the cosmos? What would it do to philosophy, to religion, to the quiet existential question that has lived in the human chest since the first night someone looked up and wondered whether the stars were watched from the other side? I do not think the answer is panic or chaos or the collapse of anything. I think the answer is something much quieter. I think the discovery of life elsewhere would produce in most people a feeling they would not have predicted. Not terror, not displacement, but something closer to relief. The relief of knowing that the universe is not empty, that the chemistry that produced us is not a singular accident, that whatever this is, being alive, being aware, being here, it is not a mistake that happened once and only once in all of space and time. Carl Sagan wrote in the last years of his life that the most poignant aspect of the search for extraterrestrial life was not the possibility of finding something frightening or overwhelming. It was the possibility of finding something familiar, of looking across the galaxy and recognizing in some alien chemistry or alien structure something that rhymes with what we are, not the same, but rhyming. And there is one more thing about the stars in the neighborhood of our sun that I want to share before we reach the end of this part of the journey, something that reframes the entire question of interstellar travel in a way that most people have never encountered. The sun is not isolated. It belongs to a loose extended family of stars called the solar neighborhood within roughly 15 to 20 light years of our sun. Within that neighborhood, there are approximately 50 known stellar systems containing roughly 60 individual stars. Of those, a significant number are red dwarfs with confirmed or candidate planets in their habitable zones. TRAPPIST, one about 40 light years away, has 3 confirmed habitable zone planets. Tau Ceti, about 12 light years away, has candidate planets in its habitable zone. Wolf 1061, about 14 light years away, has a confirmed rocky planet in its habitable zone. The solar neighborhood, it turns out, is not an empty wasteland between rare islands of activity. It is dotted with destinations, some of them rocky, some of them the right distance from their stars, some of them perhaps carrying the right ingredients for the chemistry of persistence, the chemistry that, given enough time and enough stability, sometimes produces something that looks up at its own night sky and asks, "Is anyone out there?" The distance remains what it is. 1 light year is still 5.88 trillion miles. Proxima Centauri is still 4.24 of them away. But the universe has been quietly showing us through every telescope we turn toward it that the investment would not be reaching for emptiness. It would be reaching for something. And that something is reaching back in light across the dark, and all we have to do is learn to read what it is saying, what it says when we finally have the instruments to hear it fully, and what it means for the strange, brief, radiant thing that we are. That is where this whole journey has been leading, and it begins with a truth so simple, so old, and so personally addressed that you may have felt it before you had the words for it. There is a photograph taken in 1990 that changed the way I think about everything we have discussed tonight. Not the pale blue dot we touched on that earlier, and you already carry it somewhere inside you now. A different photograph. One that most people have never seen, and that deserves far more attention than it receives. It is called the Hubble Deep Field. In December 1995, astronomers pointed the Hubble Space Telescope at a patch of sky near the Big Dipper, a patch carefully chosen because it contained almost nothing. No bright stars, no known galaxies, just a small square of what appeared to every previous instrument to be empty darkness. The patch was about 1/24 millionth of the total sky. If you held a grain of sand at arm's length, it would cover roughly that much of the sky above you. They pointed Hubble at that grain of sand-sized patch of apparent emptiness for 10 consecutive days. What came back was not emptiness. What came back was approximately 3,000 galaxies. 3,000 entire galaxies each, containing hundreds of billions of stars packed into a square of sky so small you could cover it with a grain of sand held at arm's length. Every point of light in that image was not a star. It was a galaxy. 100 billion stars at minimum, compressed by distance into a single pixel. And that was 1 grain of sand out of every grain of sand on every beach on Earth. Take a breath. We are going somewhere with this. And where we are going is not outward, it is inward, it is home. We have spent this entire journey moving in one direction outward, measuring, calculating, building scale models in the imagination, stacking light years like coins watching numbers grow, until they exceeded every frame of reference the human mind normally uses. We have walked to the stars in our minds and found the walk takes 192 million years. We have built the fastest things our species has ever made and found them still achingly slow against the dark. We have bent time with Einstein's equations and found that even relativity, generous as it is to the traveler, cannot give back what the journey costs. But I want to spend this final part of our night together doing something different. I want to reverse the direction entirely. Not outward, but inward. Not forward through space, but backward through time. Because the most astonishing fact about a light year, the fact that tends to arrive last after all the calculations are done, after the numbers have settled, is not about the distance. It is about what the distance means for the light that is already here. Every photon currently entering your eyes from any star in the night sky is a traveler. It began its journey somewhere else at some other time, moving at 186,000 miles per second through a vacuum so empty and cold that the word empty barely begins to describe it. It traveled alone, without slowing, without rest, through a darkness that has no landmarks, no mileposts, no sign that anything exists until it arrives at something that can receive it. And then it hit your retina. You are right now the destination of light that has been traveling for years, for decades, for centuries or millennia, depending on which star you were looking at. The universe sent these photons before you were born, before your parents were born, before the country you live in existed, and they arrived tonight at you. Specifically because you were in that particular spot at that particular moment, with your eyes open and your face turned upward. This is not a metaphor. This is physics. And it is, I think, one of the most quietly extraordinary things about being a conscious creature in this particular universe. Now, let me tell you something about starlight that most people learn in passing and then forget, because they have not been given the right frame for it. The light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means that if the sun were to somehow vanish at this exact moment, simply cease to exist, which is physically impossible but useful as a thought experiment, we would not know for 8 minutes and 20 seconds. We would continue to experience sunshine, continue to feel warmth, continue to see the blue sky for over 8 minutes after the source was gone. We would be living in the afterglow of something that no longer existed, and we would have no way of knowing it. Now, extend that principle to the stars. The star Sirius, the brightest star in the night sky, is about 8.6 light years away. The light you see when you look at Sirius left that star 8.6 years ago. Sirius, as it appears to you tonight, is Sirius as it was in 2016 or 2017. You are seeing its past. The star Betelgeuse, the red supergiant in the shoulder of Orion, is approximately 700 light years away. When you look at Betelgeuse, you are seeing light that left it around the year 1325. At that moment, the Black Death was spreading across Europe. The Aztec civilization was beginning to form in central Mexico. Dante Alighieri had just completed the Divine Comedy. The light that carried the image of Betelgeuse into your eyes tonight began its journey in that world and traveled without pause through every year of human history that followed through the Renaissance, through the Age of Exploration, through the Industrial Revolution, through 2 world wars, through the moon landing, through the invention of the internet, and arrived here tonight for you. The Andromeda Galaxy, visible on a dark night as a faint smear near the constellation Cassiopeia, is 2.537 million light-years away. You are seeing Andromeda as it was 2.537 million years ago, when our ancestors were small-brained, stone-tool-using hominids who had not yet discovered fire, had not yet developed language, and had not yet begun the journey that would eventually produce a species capable of understanding what it means to look at a galaxy 2.537 million light-years away. The night sky is not a view of the present. It is a museum of time. Every direction you look is a different depth of the past, all arriving simultaneously, all colliding at the back of your eye in a single moment that feels like now. Here is what I think about when I hold all of this together, and I want to ask you something genuine before I continue. Does knowing this make the universe feel more distant or more present? Does the fact that you were seeing Betelgeuse as it was in 1325 make that star feel more remote from you? Or does it create a kind of intimacy? The sense that you are receiving a message, however unintentional, from something that was shining long before you arrived and sent its light ahead, like a letter that took 7 centuries to find its address? I ask, because I think the answer is different for different people. And both answers are true in their own way. The universe is both immeasurably far and surprisingly close, depending on which direction you are looking outward into space or inward into what we are made of. And what we are made of is where this story ends, or rather where it begins again. In 1957, an astrophysicist named Fred Hoyle, brilliant difficult, often wrong in spectacular ways, and occasionally right in ways that transformed science, published a paper with William Fowler and the husband and wife team of Jeffrey and Margaret Burbidge, outlining the nuclear processes by which stars synthesize chemical elements from hydrogen and helium. The paper is known in astrophysics by its author's initials, B2FH. It is one of the foundational documents of modern astrophysics. What B squared, FH established with mathematical precision, is something that has since become one of the most widely quoted scientific facts in popular culture, usually quoted correctly, but rarely explained with the depth it deserves. Every heavy element in your body, every atom of carbon in your DNA, every atom of oxygen in your blood, every atom of calcium in your bones, every atom of iron in your hemoglobin that carries oxygen to your brain at this exact moment was forged inside a star. Not a metaphor, not poetry. Literal nuclear alchemy performed in the cores of stars under conditions of temperature and pressure so extreme that the word extreme loses meaning, temperatures in the hundreds of millions of degrees. Pressures that make the core of a nuclear bomb look gentle. In those conditions, simple hydrogen nuclei are fused together step by step into increasingly complex elements. Helium, then carbon, then oxygen, then neon, then silicon, then iron. Iron is where the fusion chain stops. Iron nuclei cannot release energy by fusing further. And when a massive star's core converts entirely to iron, the fusion reactions that have been supporting the star against its own gravity for millions of years suddenly fail. And the star collapses, then explodes in a supernova so bright it can outshine an entire galaxy for weeks. That explosion is not a destruction, it is a dispersal. The elements forged over millions of years in the star's interior are scattered across light years of space in a matter of hours. Carbon, oxygen, nitrogen, calcium, iron, and dozens of other elements expanding outward in a shock wave that eventually slows, cools, and mingles with the surrounding interstellar gas and dust. Over millions of years, gravity slowly gathers that enriched cloud into clumps. The clumps condense. New stars form. Around some of those new stars, the leftover debris, now rich in heavy elements that were absent in the universe's first generations of stars, coalesces into planets, rocky planets. Planets with iron cores and silicate mantles, and on at least one of them oceans of liquid water. And in those oceans, after another billion years or so, chemistry finds a way to organize itself into something that replicates, that adapts, that eventually develops a nervous system capable of looking at the night sky and tracing the path that led from an exploding star to a human eye. You are not made from stardust in the loose poetic sense that phrase is sometimes used. You are made from stardust in the precise nuclear physics peer-reviewed sense. The iron in your blood was manufactured in the core of a star that died before the sun was born. The carbon that forms the backbone of every molecule of your DNA was assembled in stellar interiors over millions of years. You are, in the most rigorous scientific meaning of the phrase, a rearrangement of star. Now, hold that against everything we have calculated tonight. We said it would take a walking human 192 million years to cross 1 light year. We said our fastest spacecraft would need 1,550 years. We marveled at the distances, at the silence between stars, at the biological cost of interstellar travel, at the engineering challenges that dwarf anything our civilization has yet attempted. And all of that is true. Every calculation stands. But here is what is also true. The matter that makes you has already made the journey, not recently, not in a way you could perceive or remember. But the atoms in your body were once dispersed across interstellar space. They were once part of that vast, cold, dark medium between stars. The same medium Voyager 1 is now traveling through the same void that would challenge any interstellar traveler, the same emptiness that makes a light year feel so crushing when you stare at it as a number. Your atoms have already been there. They made the crossing. They drifted through the interstellar medium for millions of years before gravity gathered them into the cloud that became the sun and the earth. And here they are, now temporarily assembled into a form complex enough to be aware that it is made of star. You did not need to travel to the stars. The stars traveled to you. They sent their substance ahead billions of years ago, and you are the result. There is a physicist named Neil deGrasse Tyson, who has a line I have always found useful not as poetry, but as a compressed scientific argument. He says, "We are not figuratively, but literally stardust." And then he adds something that I think is even more important. We are in the universe, and the universe is in us. That second part is the one I want you to carry tonight, because it contains the answer to the question this whole journey has been circling. The question of whether the distance means we are small. It does not. Here is why. The light year is not a measure of our limitation. It is a measure of the scale of the system that produced us. The universe needed to be roughly 13.8 billion years old to have had enough stellar generations to forge the heavy elements life requires. It needed to be large enough, and therefore, because expansion and time are linked old enough to have the matter spread across the distances we observe. The vastness is not incidental to our existence. The vastness is the condition for our existence. We could not exist in a small young universe. We require the scale. Every light year of distance is evidence of the age and scale that made us possible. We look out at the immensity and feel small, but the immensity is precisely what we are made of. The distance is not between us and the universe. The distance is part of us. Let me close with something that happened in 1977, the same year Voyager launched as it happens, which feels appropriate. A graduate student named Charles Lineweaver, who would go on to become a professor of astrophysics and astrobiology at the Australian National University, has written about what he calls the cosmic perspective, the shift in self-understanding that comes from genuinely absorbing the scale of the universe, not as an intellectual exercise, but as something felt. He describes standing outside on a clear night and really trying to understand that the faint smear of the Milky Way above him is not a decoration on the sky, but a structure. He is inside a flat disk of 200 to 400 billion stars, with the sun located about 26,000 light years from the center orbiting that center at roughly 514,000 miles per hour, completing one orbit approximately every 225 million years. We are not looking at the Milky Way. We are in it. We are moving through it at 500,000 miles per hour on a planet that is also moving around a star that is also moving, and we feel none of it because the scales of space and time involved are so far outside the range of human sensation that we default to feeling still. But we are not still. Nothing is still. The universe is in continuous extraordinary motion at every scale, from the electrons orbiting the nuclei in your cells to the superclusters of galaxies moving toward the Great Attractor, a concentration of mass roughly 150 million light-years away that is pulling our entire local group of galaxies toward it at roughly 14 million miles per hour. Everything is going somewhere. Everything is already in motion. The journey in every sense has been underway for 13.8 billion years. We simply became aware of it recently. So, when someone asks how long would it take humans to cross a light year, there are several true answers. There is the honest physical answer at a walking pace, 192 million years. At our fastest current technology, around 1,550 years. At relativistic speeds not yet achievable, perhaps a few subjective years for the traveler while decades pass outside. There is the biological answer longer than any current human body could endure without extraordinary intervention, medical, technological, or evolutionary. There is the engineering answer. We are perhaps a century or two from the earliest theoretical capability to send tiny robotic probes at meaningful fractions of the speed of light, and perhaps much longer from sending anything human. But there is also a fourth answer, and it is the one I want to leave with you tonight. The light year is not a wall, it is a horizon. And every horizon in human history, when approached with enough patience, enough ingenuity, and enough willingness to take the next step before knowing where the step after that will land, has eventually revealed what lies beyond it. The ocean was a horizon once. The stratosphere was a horizon once. The sound barrier was a horizon once. In each case, the people who crossed it were not the people who were certain they could. They were the people who were uncertain and went anyway. The stars are the next horizon. They are not waiting to be conquered. They are waiting to be known, the way you might want to know a stranger whose face you have seen from a distance, who looks from far away as though they have something to tell you. We are the species that looked up at the night sky and, rather than simply accepting the beauty of it, decided to ask what was actually there. That question is not a small one. It is not a comfortable one. It requires calculations that produce numbers too large to feel distances, that dwarf every scale the human body naturally understands, and timelines that stretch far beyond any single life. But the question itself is very human. It is perhaps the most human thing we do. We look at the horizon and we ask, what is beyond that? And then slowly, generation by generation, we find out. Tonight we followed that question from a walking pace to the edge of what physics permits. We counted the generations it would take to walk between stars. We rode along with Voyager as it drifted into the silence beyond the solar system. We bent time with Einstein, weighed the cost to the body, dreamed with the generation shipbuilders, and looked through the eyes of the James Webb Telescope at a universe that turns out to be far less empty than it appears. And we ended here at the realization that the atoms in your body have already been between the stars, that the distance is not a barrier between you and the cosmos, that you are the cosmos temporarily folded into a shape that wonders about its own origin. That is not a small thing to be. That is, in fact, the most extraordinary thing in the known universe. Thank you for spending this night with me. Thank you for keeping your eyes open long enough and your curiosity alive long enough to follow this question all the way from a comfortable chair to the edge of a light year and back. These quiet hours, the ones we spend not scrolling, not rushing, but simply listening to the universe describe itself, are some of the most genuinely valuable hours a mind can spend. I am grateful you spent some of them here. If this journey brought you something wonder or calm, or simply the pleasant disorientation of feeling small in a good way, share it with someone who might need that feeling tonight. And when the next question comes, because there is always a next question, always another horizon just past the one we just crossed, I hope you will be here to follow it. The universe is full of stories. We have barely begun. Sleep well, dream of stars, and remember, you are already made of them.